We have a child who pushes a toy railway carriage with a mass of 40 grams, causing it to move along a horizontal section of the track at a certain speed. The carriage then moves up the incline to reach the horizontal part of the track, 100 millimeters above PQ. Calculate the velocity of the toy carriage while traveling along RS, and all effects of friction can be ignored. So the first thing we're going to do is we're going to say that mechanical energy at the top, or rather let's start with the bottom because the bottom is on the left, is equal to the mechanical energy at the top. And so as a result, what we're going to do is we're going to say that mechanical energy is actually kinetic energy plus potential energy, and in both cases. What information do we have about this kinetic energy? We can say it's a half. We need to change that 40 grams into kilograms, so it's 0,04. We've been given a speed at the bottom, 1,5, and we know that at the bottom it had no potential energy, so we can say 0. I've nearly made the mistake that you guys keep making. I've nearly forgot to square that, so you mustn't forget. Kinetic energy is a half mv squared. Okay, so you've got to square the velocity. The kinetic energy is a half the mass, 0,04. You don't know v, and it's squared. And the potential energy is 0,04, 9,8. And then we need to change this 100 millimeters into 0,1 meters. When I resolve all of that, and I don't forget to square root the v at the end, I get 0,54 meters per second. We've got a bullet of mass 100 grams traveling at a certain speed. It strikes this piece of wood that's resting, and the bullet becomes embedded, and they move off together. So not terribly difficult. Let's see what we can do with that information. The first thing is that we need to say that total linear momentum is conserved. And we need to say that momentum before is equal to momentum after. What information do I have? I have got a 100 gram is 0,1 kilograms bullet, so it's 0,1. Its speed is given to me at 260 meters per second, and the block is standing still, so it's got no momentum. We've then got a velocity afterwards of the two. Well, first we need to put these two together, so it's 2,6, which is 2,5 plus 0,1, multiplied by some other velocity that I do not know, and I find that that velocity turns out conveniently to be 10 meters per second. Calculate the kinetic energy. EK is equal to a half mv squared. So that's equal to a half 2,6, 10 squared, and it turns out to be 130 joules. And the next one is we've got energy being transferred. Using the concept of conservation of energy, calculate the distance the block must plus the bullet, so together, travel before stopping. Assume that they are slowed down by a frictional force of 65 newtons. What happens to the kinetic energy possessed by the block as it slows to stop? Well, firstly, we know it's going to get converted into heat energy because of the contact of friction. There's probably a little bit of a sound. I mean, you'll get as it comes to a stop. So now let's take a look and see what we can do with this 130 joules of energy. We do know that work done is energy transferred. We've got the kinetic energy that's being transferred. I have 130. I need to get to 0. So in other words, I'm going to say that the work done is 130 minus 0, and that is going to be equal to the force exerted times the distance. And the force exerted is 65 newtons, they tell me that, and therefore the distance is going to turn out to be 2 meters. A toy cart has a mass of 8 kilograms, and is traveling at 5 meters per second towards the swinging block over here. It hits the 2 kilogram block, which is attached to the ceiling, and the cart collides with the block, and thereafter it moves off in its original direction at a new speed, while the block is swinging up above the ground and above the trolley. So the trolley is going to kind of go past there before the block comes back. Differentiate between an elastic and an inelastic collision. This is very important. In both types of collisions, momentum is conserved. In an inelastic collision, kinetic energy is not conserved, whilst in an elastic collision, kinetic energy is conserved. And what's important is to realize elastic collisions only happen when the two objects separate from one another. So in this one, they do separate from each other. There was a hit, it went away, and this continues to move. So it might be an elastic collision. Let's see what we get to. In order to determine the height, two conservation laws are going to have to be applied. Name them. Now, the first thing that happens is we've got a collision. Conservation of momentum. Then you have all the energy at the bottom being transferred into energy at the top. So that's conservation of energy. So those are the two laws you're going to do. Neglecting the effects of air friction, determine the height which the block swings to by using these two conservation laws. So let's go. Starting with linear momentum. We are going to say total linear momentum is conserved. And therefore we can say that the mass times the velocity of each of the objects before is equal to that afterwards. So I'm going to say 2 kilograms was stationary, 8 kilograms was, sorry, that's a plus sign, 8 kilograms was moving at 5 meters per second. That will be equal to 8 kilograms is moving at 3 meters per second. Notice that they both have the same direction and therefore the same sign, and I've chosen it to be positive. And we can certainly see that this block must move off to the left as well, so its direction is also going to be the same, plus 2, because that's the mass of the block, and some more other velocity that I do not know. When I resolve that, I find that that velocity turns out to be 8 meters per second. And it's obviously, if it's a velocity, it needs a direction, and it's to the left, because it has the same sign as the other two. Plus, I can see it in the picture. But anyway, carrying on. The next thing that happens is I need to say that kinetic energy is conserved, and I can say, sorry, mechanical energy is conserved. The kinetic energy at the bottom is equal to the potential energy at the top. What's going to happen now is I'm going to say a half of the mass of just the block now, that's the only thing that's going up there, times its height, which I do not know, times its velocity, kinetic energy, squared is equal to its mass times 9,8 times some more other height that I do not know. When I resolve that, the height is going to turn out to be, it's going to be 3,27 meters, if you prefer, better than just 2. So that's the height.